Hey, Alex Williams of the New Stack here today with Josh Wood, DocOps guy at CoreOS. I was asking you earlier about that title. What does that mean, DocOps?
Well, that's our sort of clever play on the DevOps trendiness. We just wanted to make the documentation department here at our little startup sound a lot cooler. So in short, I am in charge of documentation and a lot of public communication stuff here at CoreOS.
Awesome.
So sort of a technical writer, if you really want to, be grounded about it.
Hey, I gotta respect a fellow writer here. So good to have you.
Well, thanks for having us, certainly, Alex.
So we're going to talk about all things Rocket today, the container technology that CoreOS has been a big part of developing.
Indeed, and I'm hope through a couple of short demos to kind of show some of the whys and wherefores of Rocket, the things that drive Rocket's design, and sort of give a little taste of what it feels like to use the software. And then I hope we'll discuss some of like why we built Rocket and why we sort of are pursuing these goals with this container runtime.
Excellent. So why don't we get right into the demo, and I will have plenty of questions along the way.
Excellent. Sounds good. So let me get my screen sharing up here. And I think we should be looking at a simple terminal window. Rocket is implemented as a very simple command line utility in what we like to think of as the finest Unix traditions. It does not actually implement an interposed daemon like you may be more familiar with in the Docker process model.
Mm-hmm.
So Rocket actually is just a simple command line tool that does the job of setting up isolation environments for a container and setting it spinning in execution. Then Rocket actually exits and is no longer in between the container and like standard system management tools like an init system or systemd.
So that speaks to the heart and core of what differentiates Rocket, doesn't it?
Yeah, I think especially so. I think the dedication to making it a much smaller, more modular, composable set of tools separates the Rocket architecture and implementation from what we see in Docker. At the same time, I think that the two projects are friendly and competitive in very healthy ways for both of us in that over the time since we first announced Rocket, you've seen Docker make some of the same moves to try to retroactively adjust what is currently a fairly monolithic architecture to break it out into smaller pieces and maybe end up in a place where that architecture looks a little bit more like the Rocket architecture has from the very beginning. And I think in the same way, activities in their container format and some of their approaches to super simple networking stories on like the developer laptop and the development scenario have inspired some of the things that we're working on really hard in making the kind of Rocket container build process a little bit simpler and more fun story for just a developer on a laptop doing sort of ad hoc development, which is something we think the Docker side of this equation is very good at. Excellent. So I think the two projects kind of feed and inspire one another, yeah.
Great.
So actually, to continue into just a little miniature Rocket demo for folks that maybe haven't seen the software before, Rocket has a cute command line Unixy name, rkt, Rocket. And that just implements basically a set of functions for querying the state of and setting up the execution of container images. Now, Rocket is itself an implementation of the ACI container image format, which is a different image format than the Docker image format. And while the Rocket development and build story and Rocket's native image format is that ACI container, Rocket does have full support for Docker containers, and we can actually fetch them directly from Docker Hub by just adjusting the sort of standard Rocket run commands. So let me sort of do a quick three-stage demo. First, let's look at Rocket running a pretty standard and already ACI formatted container that we keep at our Quay.io image repository, which right now is the only public repository I know of that can serve both Docker and ACI images, and in fact convert between them on the fly for different use cases. So anyway, first thing I'm going to do here is run a little simple Alpine Linux container that we keep for kind of
Alpine,
demonstration.
huh?
Yeah, purposes.
So tell us about that decision. I'm curious about that.
So I assume you refer to the Docker decision to begin driving Alpine as a standard from image, right? A base image.
Yeah.
Yeah, and I think that's very interesting because I think it speaks a lot to something we've. I know that my colleague here at CoreOS, Brian Harrington, has given in several places over the last year or so a talk he calls minimal containers.
Right.
And while an Alpine container is still not quite as minimal as what we mean when we say minimal containers, it is a great step forward versus carrying a Ubuntu or a Debian around underneath what amounts to a lot of times just a single binary that actually constitutes the active code for the application that container is concerned with. So we like anything that makes containers smaller. We think containers ought to be very dedicated in purpose, and when possible, we build our containers with statically linked single binaries. But Alpine is a step in that direction, and so we were happy to see Docker sort of start encouraging folks to use that. And I think they also hired the developer from Alpine, right? He's a fellow we think a lot of and have enjoyed his work. So this kind of lightweight Linux is definitely neat for doing, Linux in a container demos, and that's something we do all the time with CoreOS. So
We could have conversations all day long about what that lightweight technology actually means then for scaling out, because now this raises all kinds of other interesting density questions, doesn't it? And
yeah, actually, it does.
manageability.
And we also see it not only on the density question, which is certainly an important element of this, because the facts are, if I want to pack 10,000 containers onto a really large piece of hardware or a rack section, the individual size of each of those containers starts to become really important, both in memory and even just on disk. Memory is probably the most constrained of all resources in cloud environments. And so the impact of really large library linkages and really large C libraries and sort of these full-scale, full-weight Linuxes that we've carried into these first and second generation containers, I think there's a lot of pressure to get that to go away. And so we try to construct a lot of very single-purpose containers here at CoreOS. And this is a little bit of an aside, but it's a really good time to mention it, I think. Rocket actually organizes execution around something we call a pod, the same unit of execution that the Kubernetes cluster orchestrator uses. So not only is it just convenient to have that one-to-one mapping, what it means is when you build really minimal containers, the pod gives you a way to controllably share resources among them to make those kind of really micro-scaled architectures make sense and work in fluid ways and be open to combinations with other very minimal containers. So that pod artifact is then sort of how you take these really simple bits that you've managed to break things out to and build them back into units that provide a service as a user would understand it, perhaps.
There's so much there. I mean, I could ask you 20. I could ask you 20 more questions on this. I mean, and because this gets into issues such as I/O patterns, right? And
Very much so.
How do you manage the memory? What are
Indeed. And most of that also, if we wanted to really have technical fun with it, we can discuss how we're almost always talking about this in a virtualized environment where all of that memory has been overcommitted by the hypervisor in the first place. So there is a really interesting dimension there. Yeah. But even before if we dive any deeper into that, we may never get out. So I will the second part, which is, something that's a mantra for us at CoreOS is frequency and consistency of software updates. We believe in containers and we believe in this minimal operating system because by decoupling those two and dissolving the dependencies they have formerly had on one another, we can really frequently update an operating system and gather all the security patches right up to the latest second without affecting applications that a few years ago would have broken every time or needed regression testing every time, because we've turned that application into something self-contained in a minimal container. And we've done the same thing with the OS. We can upgrade them really frequently. Well, the next part of that story is the larger your containers are and the farther you have to move them over the wire, the less likely you're going to be to update them. So that is actually another piece of that minimal container story. If we're going to be really small and your transatlantic links may not be that fast, So, we want those updates to happen and really ride the leading edge of that wave of security, because right now that is the solution to keeping internet infrastructure and internet application software secure, is that constant and frequent ability to update.
The wire still matters.
Indeed. Indeed. So if I will actually come back a little bit to the demo, and we should at least look at Rocket running a container or two and kind of show folks the differences. So if we come back to my screen here, we notice I'm sitting in a command line, and I'm about to issue a Rocket run command. Now, you just saw me go back and type sudo, and so I'm going to digress once again and talk a little bit about permission structuring in Rocket and the principle of least privilege. The thing you are about to watch me do, and which my demos will be mostly concerned with, which is running containers. As I've just started one running and pulling now, so it can go on and do that while I talk in the background. Oh, sorry. We'll actually have to go back to that. So I see what I did. It's a misspelling. Very simple. So once again, we'll pull this. And now we're sitting at the command line inside of this Alpine container. And you can see that very easily by doing a PS list and seeing that we're in a much restricted process space compared to that we would see on the host. Now, at any rate, the thing that I wanted to mention here as I started out the demo is Rocket, again, has just set up the C groups, the network namespaces, and made a connection for that interactive terminal that I requested with this particular command line option to connect me to the standard input and output of this container. But once it has done those things, it actually performs an exec on the main process in the container, which in this Alpine Linux is the shell process right here, and then exits and gets out of the way. So if I take a look at, we can see here what the internal process view inside the container, inside of Alpine's world looks like. If I come back out here to this is the main host that we're running this Rocket container on. So first of all, I can use a Rocket utility to list for me the containers that are running. This is very analogous to a Docker PS. A similar command lists the images that we have pulled from which those containers are executed. But maybe more interestingly, we can take a look at what the process tree on the host looks like. And we can find this shell that we just kicked off running inside of what is literally an illustration in hierarchical terms of what we call the Rocket process model. And you notice something that isn't in that list is Rocket. Rocket spins up an init system. That's just actually a stub systemd inside of the container to manage process life cycles. So you don't have to re-implement init to manage processes inside of your containers. We leverage that stub systemd to give host level systemd visibility into and control of these processes as if they were normal service processes running on the host. So if you look at the output from our systemctl status command, once again, you can actually see an entire machine slice devoted to our Alpine container, containing the systemd stub that manages process life cycles inside that container, and then the shell and the PS tree essentially that we looked at from within the container is listed right there under systemd control and is a first-class entity for systemd monitoring, restarting in the event of failure, and managing the whole life cycle of the larger container as a process on the host. So that's a lot of what falls out of that design of Rocket being demonless, or as I like to say, we've given it an exorcism.
So this is a real differentiator, isn't it? And why was this architectural decision made to follow systemd? I mean, I know it may be relevant to a subset of the community out there, but I'm just curious.
Well, first of all, we have always tried to use sort of what we view as the latest, greatest Linux stack. So to that end, CoreOS has a really up-to-date, darn near bleeding edge Linux kernel under the alpha versions, and then obviously tested ones that are a little bit older, moving back to stable. But we do the same thing with the very narrow set of system software that we ship above that kernel. And at the time of our inception, about 2.5, 3 years ago, when we really first started thinking about how to build CoreOS and what it ought to be, Even though systemd was controversial, it definitely contained a lot of answers to questions we were already beginning to ask about how you connect the orchestration level of large cluster operations to the actual control of nodes that are members of that cluster. Systemd has a lot of neat facilities for describing dependencies in a way that can actually capture the complexities of the systems we're constructing today that maybe like Sys5 init and earlier approaches to this didn't necessarily have all of these facilities. So we very much built CoreOS around systemd, and one of the other reasons we did that is that for better or worse, and even though this is sometimes one of its controversial features, systemd sort of swallowed a lot of basic Linux system services. And by using systemd, we sort of get network control services, time synchronization services, and journal aggregation services all as part of this one package instead of as what might be larger components if they came from multiple sources as they used to, say, just before systemd. So that was another kind of neat feature that fell out of it. So given that platform on CoreOS, and because Rocket was designed primarily for CoreOS and other very modern Linuxes like it, it was natural to want to have an architecture that would allow us to leverage all of that same system management stuff. You know, we really didn't want to abandon that. And more than anything, I mean, the best thing I can say about it probably is we really didn't want to add to the pattern of people like Yelp and other poor folks feeling that they had to literally re-implement init, one of the oldest, perhaps the oldest user-level executable on a Unix system. You know, the thing Ken Thompson wrote right after he wrote the kernel. We hate to think that somebody has to re-implement that just to manage processes inside of a container, just because of the architecture of how that container environment's set up. And so by combining sort of that philosophy with the set of tools systemd already gave us, we were really able to drive a lot of these things actually directly out of systemd. Much of the C group management and setup stuff is actually really just very lightweight communication between Rocket and systemd setting up that initial container isolation environment.
Okay, great.
So yeah, and you know, one of the other neat things I can kind of show folks about that, I always find this a little bit interesting because we get a lot of questions, you know, depending on the event and sort of the level of the audience. There are people, this is a really new world, and we see, you know, there are people all along the sort of spectrum of learning about it, and we get like a lot of questions of how is a container different from a virtual machine is a question I hear sort of at conferences and stuff sometimes. So I always like to show this little machine control demo. Because Machine Cuddle, of course, is a systemd utility designed to control virtual machines as first-class service entities on their host. But you'll notice we have two quote-unquote virtual machines listed when I invoke Machine Cuddle, and they are the two Rocket containers that I have started. One just before this demo that I forgot to clean up, and the one that you saw me start in this demo. So you can see sort of by UUID, the same person, an entity that I know from a Rocket list as this executing container, has these other host level service management handles directly available to systemd, and that actually allows you from small scale to large scale really to kind of script and do a lot of neat things without really creating a whole lot more infrastructure, because a lot of it's already there. So another neat thing that might be, like, I think if we've had sort of an illustration of the Rocket process model in depth, and really kind of showing the big difference between it and some of the other container management engines we've seen. Right. I think one of the things that's most interesting is we have been committed in sort of along the same lines that I was talking about earlier, in the way we believe these two projects, Rocket and Docker, are very good at inspiring and challenging each other to new innovations and stuff. We've always been committed to Docker image compatibility until such time as we can drive a common standard so that there's no such thing as compatibility, because we're all using a common image standard. So to that end, one of the nifty things Rocket can do in an almost deceptively simple way with this little URL prefix here is actually just fetch Docker images from Docker Hub, convert them on the fly, and run them for you. So I've left out one more word here. I apologize. We actually have to tell it what we want it to do. We need a subcommand. So
Right.
rocket run, rather than no subcommand, we'll actually go grab, Caddy is a web server built by a friend of ours here, Matt Holt. It's written in Go. We can compile it statically. It's very lightweight, so we love it for sort of containerization demos. And I have a package, a Docker container ready-made that's sitting on the Docker Hub that I use for these sorts of things, and that is where I'm pointing the rocket run command right now. So
That's CADDY, yeah, caddy, right.
And we would love to have a big graphical showcase for the demo, but that's actually how simple it is. I have just spun up a web server. It is listening on port 2015, as you can see in its last report to standard out here. Now, I have not bothered to set up a network or any routes to the outside world for the purposes of this demonstration. So it is worth a moment to note that there are a variety of flexible network configuration commands in Rocket, and Rocket actually leverages another project of CoreOS's called CNI, the Container Network Interface, to perform these network manipulations and do things like set up bridges between the host interface to route traffic into service-providing containers, which is definitely the pattern you would probably use with Caddy, a web server, and additionally to set up routes to the outside world or elsewhere in the infrastructure. CNI is a plugin system that means you have your choice of SDN and NFV network provisors that can implement a very simple interface to the CNI library and then have automatic integration after that with systems like Rocket. And I should also mention that CNI is the network plugin model for Kubernetes, our and Google's project for cluster orchestration. So supporting CNI gives your SDN or your network virtualized firewall software a direct route to supporting these two increasingly important applications.
So the CNI, what's the importance of that for you guys, and why tell me about it? Seems like it's quite relevant to like what you're talking about before, about the security, in many respects.
Well, it is. I believe it does have a security story, but probably in its initial phases, and we have merged it with Kubernetes and sort of officially endorsed it as the Kubernetes network model for network plugins in the fairly recent past, like in the order of the last couple of months. And so kind of in the early stages, I think our focus is really about it making it much more convenient to satisfy an increasing demand we hear from customers and partners, which is hybrid deployments are happening. People are reserving high performance work or high security work for their on-premises data centers and shipping commodity work to commodity cloud providers that they may have better economics on for that sort of commodity work. And I don't want to get too far into that and try to break it down into something specific for a given industry, but you can imagine a financial services house may have certain records that need near real-time processing or have extremely stringent security requirements, but other records may not, and they may simply use cloud services for those things. If that's really going to work, one of the real pain points for our in-the-field integrators and other customers we talk to and developers is simply configuring the dizzying array of networks and network and IP address management policies that are available between these multiple cloud providers and people's own data centers that may have long-standing authentication integration requirements or certain ways that IP addresses are issued on the basis of MAC addresses or host UUIDs. Rather than trying to adapt Rocket and Kubernetes to fit with every single one of these possible models, we thought that this was exactly the kind of problem in computer science that really calls for an interface. So CNI should, at its best, and be like a VFS, like the virtual file system was for Unix decades ago. Applications running on a Unix system are able to make a very simple standard set of calls: read, write, open, close, remove, and manipulate files that way on permanent storage without caring about whether the underlying permanent storage is formatted with X2, X4, a journaling file system, NTFS, HFS. So each of those file systems writes a plugin that satisfies those 4 or 5 basic file calls, and then applications just use the VFS to perform those file operations. Well, we want CNI to operate in very much the same way. To take an example directly from our own projects, we have a software-defined networking project called Flannel. It's pretty popular in the open source community. It's pretty neat automatic setup of container networks without digging real deep into what it is. But it also comes now with a CNI plugin, and by simply using this little bitty shim of interface in the CNI, all kinds of orchestration systems that have never even heard of Flannel can potentially have Flannel configuring their container networks for them. Because Flannel simply has to tell CNI the name of a container and the name of the network it joined it to. That is literally the entire composition of that interface. And that is, by convention, enough then for the top-side users of CNI to understand what they need to know about the networks and adjust their routing tables accordingly.
So I'm looking at your blog on this, written by Stefan last month, and
Yes, yeah.
You talk about how there's now integrated support for CNI. There's now integrated support with CNI for Project Calico and Weaveworks.
Indeed.
And there'll be updates on integration with Kubernetes. So what's the equivalent in Docker for this?
Well, in Docker, there's something called libnetwork.
Right.
Libnetwork is, at least in the view of, I think if you're trying to sort of build tools for folks to build platforms, libnetwork has a lot of neat ideas about convenience.
Mm-hmm.
But to sort of achieve that convenience, I think they have made some choices on the behalf of the person who ends up using that implementation that CNI actually, in the interest of composability and flexibility, defers to the plugins. So there's a lot more implied policy and practice in libnetwork and in that approach to configuring container networks, because first and foremost, in the simplest way, it is actually very much tied to Docker containers. And it's tied to the Docker engine's view of what a network and the fabric underlying a set of containers and execution ought to look like. CNI, on the other hand, is much more agnostic about what that container network ought to look like, in the attempt to make it much easier to fit things like Rocket and Kubernetes that use the CNI layer into multiple environments without needing to know the details of those environments. I think with libnetwork, you're sort of forced into the local global dichotomy and model that they see for networks, and in many cases that simple choice is the correct choice. But the farther you move towards sort of platform builders, integrators, and people that are sort of assembling tools into their own solutions, the more you kind of need more flexibility than you do necessarily the choice, the engineering compromise in the name of convenience that I think that maybe characterizes libnetwork a little bit more.
It was interesting stories here to evolve.
Well, they are, and it's one of the reasons why, as much as I'm happy and I challenge Docker publicly all the time, and occasionally even enjoy a joke at their expense, I also always try to drive it back to the idea that this is at its root, I think, a very productive rivalry for both of us. Docker is really good at thinking about that developer laptop story and that convenience, and their engineering decisions reflect that they have a lot of people who really do think about the user sort of at his desktop, at his laptop doing development. I think CoreOS and our backgrounds and sort of the business spaces we move in, we definitely probably think in design terms first and foremost about modularity and flexibility, and about a lot of different people using these projects and products in ways we don't necessarily anticipate. And so we try to have really generalized designs on some of these things. And I think that's neat, because I think Docker drives us to think about that developer story a little more, and has influenced like how we do things like AC build to build ACI images. And I think we are somewhat successful in driving Docker to think about the story of things at larger scale where flexibility becomes so important. And I think changes they have made in the OCI organization, in the engine itself, in runc and in libnetwork have all sort of reflected a desire on their part to move towards a more modular architecture in the future. So I think ideas go back and forth.
Yeah. The thing that I think of, and I think, it's not, it's something probably that a lot of the community thinks about is, but Docker is so dominant, right? And Docker has become this almost, it has become what a unit that people recognize, right? And so I'm just curious, you guys have built your technology on very, very well thought out, open source platforms. You're developing it with really with security in mind. You're building it kind of from a totally different perspective. How do you guys weigh that in your own decision making, or do you not, or you just follow, or you just following the course that you really think just makes most sense for the market? I would expect that's probably.
I think that we have two things in mind, and one is that there is a durable market in the infrastructure level of this industry. That as you move a little farther up the stack towards the user or the consumer or the individual developer, may be less durable, that may be more prone to the vagaries of cycles. And I think that's one of the reasons, like from even a business analysis point of view, why we're sort of drawn to the infrastructure space. And of course, as engineers, we're almost to a man and woman here at CoreOS, really sort of obsessive about these kind of things we think of as long-learned, hard-won Unix philosophies. All the things I've talked about modularity and interfaces, I think really come out of that school of thought. But in a business way, something that comes out of that same school of thought, and a lesson we feel like we've maybe learned before and do not wish to repeat, is to have anything resembling a single vendor controlling the actual specification for something that we think is important to building the next generation of infrastructure as the container is. So our efforts with AppC, our participation in OCI, the directions in which we try to lead our community, and when we get the opportunities, discuss with and influence the Docker community, are all about opening these standards up and making them true community standards like the IETF standards that built the internet. Because we want exchangeability and complete interposability between these systems. I like to say in my talks that the real proof of Rocket's design being successful in the ways we wanted it to in an engineering sense came not when I ran my first container under Rocket or even converted a Docker container with it, but when I saw sort of work in progress code at Dias for an alternate implementation of an executor for the AppC container image format. That to me proved, I mean, and I don't think they're shipping it tomorrow or anything, but there's something they had worked on that they were willing to talk about with us when I was giving a Rocket talk, that there already exists an alternate implementation of the standard is kind of the proof that we want to put into the pudding of standards. So we would like there to be, if you need a custom container image to meet some particular set of goals, what if you're running on ARM64 hardware, which is a story neither we nor Docker maybe really have a great tail to the ending for yet, but you really want to ship container images. ACI gives you a way to implement something like that, or even just implement pieces of it to use containers as just a distribution mechanism, even if you don't actually use isolation when you execute them. So we think because the container, much like the actual physical shipping container in the real world, represents a revolution in how we exchange software artifacts as developers. We think it is important that there is a standard that we, the entire internet community of users, owns and can feel real ownership for, that specifies what that container is, how high you can stack them, how much load you can put inside of them.
So the end user can then differentiate the application, which way they need to be most concerned about.
Exactly. Exactly. And, it's probably also worthwhile to note that our CoreOS's commercial products and commercial pursuits do not directly relate to making sure that everybody on Earth runs their containers with Rocket. We built Rocket so we could use it in our own tectonic stack, and that's why we've done so much work to make Rocket, as it is today, a supported alternate container executor for Kubernetes. But our business play does not actually involve locking folks into any given container engine, nor, containers are just a piece of the stack we're building, which is why we're kind of obsessive about having a standard for them, and why we're willing to push so much of that that intellectual property that we've generated in this area to the community. I mean, we have fed all of that directly into the AppC project. And had very lively discussions with Docker and many other corporate partners and competitors about how those things should go. So that's what drives that effort for us.
Interesting, and more to come. So in conclusion, what I really would like to ask is about what is the role of Rocket in this new application architectures that we're seeing, and why is this why is it relevant to the end user? What is it? Why should that third-party developer out there, who's integrating, who's building out applications, what should they take away from about Rocket? What is it about Rocket that they should really kind of, really grasp?
Excellent. Well, I think, and keeping in mind that we definitely, Rocket's end users are developers who would construct containers and run them in production, we believe. And obviously the systems integrators who might be creating those platforms to run containers on, either on premises or in cloud environments. Why does Rocket matter, and why would you bother with the trouble of using it? I think that breaks down, number one, and most importantly, to security. We think that by removing a daemon that always runs as root and listens on the network, that is first and foremost a gigantic security gain, almost without need for explanation. It should be fairly obvious why that is a gigantic security gain. Secondly, by having offline, non-server reliant signatures for cryptographically verifying the entire hashed contents of ACI images, we think that is a huge win to the deployment security story that simply isn't as mature or well thought out in competing products just yet. Docker does have the idea of notary and of image signatures. They are very server reliant, and so we don't like that for two reasons. One, we can imagine ways in which they might be defeated. We think that the client in the Docker pull scenario is a little too trusting of the server's attestation of a signature, whereas Rocket uses a GPG offline signature and doesn't need a server at all to verify an image. All you need is the ACI and the signing key. So we think that's an important part of how you actually get containers into production that is somewhat unanswered by current technologies and drove part of Rocket's development. And last but not least, we think that there's a lot of convenience and overall man hours and configuration time to be driven out of these processes by simplifying the process management structure under which we run containers. It is easier to write systemd unit files to manage Rocket services. You eliminate about 14 lines of, Docker boilerplate that we're all pretty familiar with writing. If you've used systemd to manage Docker containers, you do this exec start pre, you kill the old containers because you don't really know if they're still running or not. You delete them from the image store. You finally do the Docker run to spin up the new container. It's a much more direct route to running a Rocket container and then subsequently managing it or automatically restarting it in service failure scenarios. Each of those things is a very small win once for one developer, but becomes a very large win repeated hundreds of times across large developer teams or across large deployments. So those are the two big advantages that we think you drive out immediately, even if all you do is don't change your build process at all, continue using Docker build to build your containers, continue shipping them to Docker Hub, just run them in production with Rocket. You get a better security story and you get something more composable. When you're a little more advanced than that, the security story is still your friend, and you sort of get those features, and you can use them and move them into your infrastructure. But then the composability story becomes really, really important. You know, your entry-level developer, he maybe just wants to run a Rocket container. But once you're an advanced level developer, you maybe want to build minimal containers made out of statically compiled binaries, and then link together those 3 or 4 individual containers with a pod so that they can flexibly and selectively share resources to provide the service that they're designed to provide to the actual end user together. So it's, as you build more complex services and as sort of the sophistication of your architectures increase, we think the dividends from that modularity story really start to be pronounced.
There's a larger story here about interoperability, I think, here too. That's interesting to me. When you're talking about Docker, when you're talking about Rocket and Docker, I think it's one we can follow up with another time. Josh, thank you very much for for spending some time.
Certainly, Alex.
with us.
Always love to talk about Rocket. It is absolutely my favorite thing of the many things I get to work on here at CoreOS.
Yeah,
They're all cool, but I just really like Rocket. So,
and you speak a lot publicly about it, don't you?
I do. I have been recently giving a lot of talks and answering questions and stuff about Rocket,
So
and I've seen excellent interest in it.
What's coming up? What's coming up then? Where are you going to be?
Let's see. I will be in Seattle at the Blue Box group on the 30th. So that's
Awesome.
next Wednesday, I think. Next Wednesday night, talking about Rocket and the Kubernetes integration. We do 2 cool things with Rocket. We actually bootstrap Kubernetes clusters on CoreOS with Rocket. So Rocket runs Kubernetes. And then once Kubernetes is running, Kubernetes uses Rocket as the container engine. So I always say, Rocket runs Kate's runs Rocket when you're on the CoreOS world. So yeah, that's what I'll be talking about in Seattle next week.
You must be pretty involved in the Go community too.
Somewhat so, although since I am not a line programmer, my involvement in the Go community is maybe not terribly pronounced. Certainly in the early days, because I was a major Plan 9 fan and open source contributor to Plan 9. I was maybe a little more involved in Go right around its inception, because I was very, very excited to see the Plan 9 compilers like actually in the real world for the first time. It was kind of a proud moment for everybody who had thought about Plan 9. So yeah.
But now it's all about Rocket.
Certainly.
Great. Well, Josh, it's been great talking to you. Really enjoyed the conversation, and we'll be in touch and back again soon, I'm sure, to talk about all these kinds of topics.
Well, I enjoyed it too, and definitely if we do if we want to get into sort of a Rocket Netties demo, I would be happy to come back and show you that sometime when I have my stuff together and actually have a cluster spun up.
I'd love to.
Right on.
All right, Josh,
cool.
Thanks.
Thank you.
Bye-bye.